All right, so we good? The banana is pointing to us. Okay, so all right, so we're going to march along with this madness. This is the end result. Really is dark. You're going to turn that one a little bit. That won't hurt anyone, just a little bit. No, that's no good. All right, that really is bad, isn't it? Yeah. All right.
I don't think it's that bad.
Is that all right?
I don't have glasses on, so
Let's see. Okay. So this is a rather remarkable kind of result. Right? People had no idea about this before. As I said, 2007 it was published. And the upshot is this is, writing's going to be hard here. So this is probably an edge in the system, right? This is decoupled from where it's coming from. This is just a random edge in the system. Because it's random, we don't have to think about whether it's coming from a degree k node, although you can add all those things, right? So you can add correlations between nodes and all sorts of things, but that's not what we're doing yet. Okay, so this is, as I said, so theta of the initial condition is that probably that an edge is coming from an infected node is simply probably the node is infected at time t equals 0. So those things are the same. And then we have, this is a mapping of theta t to theta t plus 1. So this helps us march along. And if we're sitting at a node, we can look at the edges around us. You know, we have 7 friends. And we can see how their probabilities get indexed up or increase of coming from an infected node. And then just along the way, right? So at each time point, we can find out what our theta t is because it's just a map. Right? Theta t goes to theta t plus 1. And every time we put theta t in here, we'll get phi of t plus 1. So phi of t is not being used, right? It's not being used. Phi of 0 is used, that's the start. But it's theta is the thing that's depending on itself. And then at every point, we kind of just siphon off an estimate of what, the actual value for this. So let's see how this thing functions in a setting that we've looked at, the Watts model, the Granover type model. And okay, so there are a bunch of things here. So R is the threshold. So these are uniform thresholds. We talked about this, uniform thresholds. Across here, this is this so-called cascade window. This thing is not on the whole screen. Is it some magical thing?
Probably the width of your screen.
No,
If
it
you
needs to be.
resize it to be less widescreen on your Mac, it'll probably fit better.
I think it's the
projector.
It's the projector. Is there a special little thing over there? See that horrible? No, that could be. Is this just too dangerous? There's that remote control thing.
Did it cut off anything like really important?
Just a lot of stuff.
All right, so here, over here is Z.
The average degree.
This thing. What does this do? Ugh. Wow. Just a few. Transparent. And then you're not even sure if it's the right one.
Transparent as generating functions.
Yeah. No, this is obviously much harder. There's a cartoon when I saw it when I was a kid. It was before I even knew what MIT was, but it was years and years ago. When it was, I think it was a non sequitur guy. And so it was in corridors, and there was a sign saying nuclear physics, subatomic, whatever, particle physics, and then this one said VCR programming. Yeah, pretty bad. So here's this original cascade window, right? So this is cascades are possible, they're not possible. This is the threshold that everyone has, and it ended at a quarter here, right? So 1 in 4, and this is the average degree of the network. So it's pure random networks. They have some average degree, and the story was as we index up an average degree, right? So we take fix a threshold, give everyone 0.18, for example, and then as we go up here, we see that there are no cascades possible. This is a threshold response function kit. contagion. Nothing's possible because it's simply not connected enough. In between here and here, we have a vulnerable component that's non-zero. That it's macroscopic, it's big. And so if you hit that guy, it can take off. And it's easy to hit in this region. It's very hard to hit at this region because it's very small. It's very small at both ends. But the peculiar thing is at this end, if you do get it, it spreads everywhere. And so this calculation tells you what that final size should be now. And we can see why it should happen. All right, so we had phi star here, z's average degree. In the paper, this paper, if you go to it, they have rho as phi and q as theta. I've tried to keep our things similar. It's for 100,000 nodes. And this piece here, okay, what's happening is this was for what this envelope here is for one initial seed being turned on. That's the majority of the focus of this was what happens if we have a fraction that are being turned on. So this was for one seed, and this is showing that they get the right analytic shape, the dash curve here. There is an odd complication we'll get to. They get because it doesn't quite fit, right? For what happens when you have some fraction. And the fraction they're turning on is 10 to the minus 2, right? So 1 in 100. That's this case up here. Okay, and then down here, this is for 3, so it's 10 to the minus 3, 10 to the minus 2, half 10 minus 2, and 10 to the minus 2. And it's not quite, why is it not there? It's for a particular value of r. So I think it's about 0.18. We could look it up. Okay, so this is the original thing where you're just triggering one guy. That's the cascade window. It looks like this, the final size. That window opens up, makes sense. You've increased the fraction. You've said, all right, now I'm going to get 1 in 1,000, right? And then a half in 1,000, and then actually, this is right. This is the original cascade window for one node. This is what happens if it's 1 in 1,000. This is if it's 1 in 500, and this is 1 in 100. So it makes sense that it's opening up like this. You still kind of get the same behavior, but the extra piece is that they're getting this. They're actually computing this final size as well.
Sorry, what are the colors showing?
Yeah, so it's intensity, the typical size of the final thing. So black means 0, and so you can see this. So this code. Okay, so this, like this guy. Hold on, this was 10 to the minus 2, 10 to the minus 2. So this is 10 to the minus 2, this one. And that fits, and we have to think about what this is. I think it's up through about here. Right, so this slice it's this slice through here. Right? So this looks like this, it goes up like that, and then it has these cliffs of insanity on this. I do want to build a whole lecture out of that particular movie. All right, so it's smooth, it ramps up, this feels okay. Disaster here, right? Or very surprising bad things here. The thing that's hidden from this is that these are unlikely events, right? It's robust yet fragile. Most of the time you don't get that. But, okay. Although when you move to, that's not good. So when you move to a fraction of infectives, things tend to take off more. The one node, which is extremely interesting case, right? That's, one thing fails and the whole power grid comes down. That's a very interesting, big, important piece. How are we doing with this, right? So it's a mixture of this, right? So you can say that. So the curves here are analytic, and the symbols are simulations. Total excitement? All right. So it doesn't quite fit, and there's a funny thing that's going on. So we have to delve a little bit deeper into what's going on here. All right. Okay, so we're going to get the basic cascade condition that we had before for the so-called Watts model and other models in general, if we take phi 0 to 0. So we're just saying it's still a fraction, right? But we're going to go to 0, and it should look like what happens when you just set off 1, because now the seeds are so far apart from each other, it starts to function more and more. And eventually, you know, they're just none, right? So this is the thing we had that we started this little lecture from. We have really a map, right? So there's some, this is a piece to think about. There's some initial condition that's put in here. So that's a parameter of this. But we have a map of the interval. Right? We're mapping theta, the probability that an edge, a random edge in this system is infected time t. Okay? Okay, so there are two ways things could take off. And so this is a nice subtlety, right? So if there are nodes that just start for free, then it always takes off, right? Because this is, so if you set 0, you say, all right, 0, there are no infected, right? The initial condition is 0, which is not quite right. I mean, these things should be the same. But let's just say at some point you're at 0, then scribble something somewhere. Really should be 0 and 0. Okay, so now you have to think about, well, what's the probability that, okay, so you have some nodes that switch on for free. So this number here is greater than 0 for some of them, for at least some k. These quantities here are all fine, right? As long as they exist, these quantities are all fine. They're just greater than, so this sum is necessarily greater than 0. So we start with 0, we go to a number greater than 0. So it makes sense. I mean, there are self-starters, the thing has to spread a little bit. So that's one possibility. Okay, then the more subtle thing, of course, is if no one's, right, there are no edges infected to start with. And we start with some fraction, and then we see if it spreads. Yeah, okay. All right. It's okay. Yeah, right. All right, so this is from our the function we had. We're interested in what happens at, so you have to figure this out. From assignment 72. You have to figure this out. But it's about the first derivative of this g function evaluated at 0. And I'll show you pictures of how this works. So if you go through and you go back to those original equations we start with, differentiate once, and look at it, you should get this collapse, right? So we'll be able to get to this from more pleasant ways, and I've structured it in a certain way. So this is the network here, right? This is probably that you connect to a degree k node. This is probably that they have, and then they have k-1 other friends. So that those two things connect. That's about the network. And this is about the contagion itself. And here's the vulnerable piece in here, bk1. Right? Probably that one of your friends is on, and you're a degree k that you get infected. And I have probably too many equations. Let me see if I can. I'm going to skip ahead to a thing, and I think they're in the right. Okay, so we're going to go back to the slides before. Is it focus okay? No, it's my head. All right. Here's this g function, right, which maps the fraction of probability that an edge is infected at time, that randomly chosen edge is infected at time t, to the probability that an edge is infected at time t plus 1, randomly chosen, right? So that's the big thing that's driving things forward. So if it looks like this, then we have a classic kind of map of the interval. It will take off, right? So if your initial condition, so remember, theta of 0 equals phi of 0, right? The fraction rows are on gives you exactly the probability that an edge is infected as well to start. They're the same. So this function is a bit funny. This is g. This is this g function. It actually depends on that initial condition too. So you can't. So you see what I mean? So maps of the interval, usually you think, okay, here's a map of interval. I can start with all sorts of initial conditions, and you think about that. The initial condition is actually forces the shape of this as well. This shape of this response function. Yeah. So this is fixed. That's an important thing. Now, if it had some kind of structure like this, it would go back the other way, and this would die out. And this is this final case where there are self-starters in here. And it doesn't matter if you start with no infected edges, it will take off. Right? So if the function looks like this, it will always take off. It gets to a finite size in the middle. A stable point, so it doesn't go beyond that. If it's above it for some reason, it will come back down. This is a case where, so this is an interesting case, this one. It's possible for a small enough initial condition that you really have something that looks like, so the slope is less than 0, it looks like it would decay. But if you start it up here, right, it takes off. Right? So you can have this kind of subtle problem here. All right, so all right, so phi infinity, the one you end up with will either be, it's the nearest stable point, right? And it's either the one that's above it, or below it, or above it, or below it, right? And this is always true, right? So adjacent stable points have opposite types, right? So this is stable, this is unstable, right? Stable, unstable, stable, unstable. And as I said, the form of G actually depends on this initial condition, right? So you can't just have any, it looks like I've got 3 initial conditions here, but that's fixed. Okay, it says the same thing. All right, so let me go back and try to put that into these equations. So we got this part. You're going to inspect this a little more and try to understand this. Okay, so you get spreading for free because some of them, right? If some people tell them for free, spreading has to occur. It just does. It may not really spread very far, but it might not actually really be spreading. There might be just these true believers, but there's a macroscopic fraction that are infected. If it has an unstable fixed point at 0, so that's the derivative of that g function at 0 is greater than 1, it takes off. Right? Chaos fans will love this.
And we do.
Okay. The appreciation. Right? Cascades are always possible. Then there's this nasty possibility that that slope is less than 1, so it's a stable fixed point, so any little seed will decay. But it could be there's an unstable fixed point just a little bit away from 0. Right, which is this case. And imagine this is a little more bunched up. Stable fixed point, so little seeds die away, but if you have a seed that's big enough, it takes off. And so that's an extra piece that's dealt with here, right? So, so it's if it's a right. So we have a non-vanishing seed. We're thinking about seeds going to 0 here, but if there's if it's a non-zero, it's a finite seed away from 0. So if it has a stable fixed point, and then an unstable one just a little bit further away, then, right, and that stable fixed point is at theta star, then for any initial condition above that stable fixed point, unstable fixed point, it takes off. So it depends on G, depends on phi 0, so it's a little bit subtle. All right, so let's, that's kind of what this story is here. How do we feel about it? Okay. The funny thing is, you're not allowed to sit here and say, "Oh, look at all these different initial conditions I can try." Once you're given the contagion, you're given the random network, you determine this iterative function of the probability, right? So that an random edge is infected, theta of t, how it grows. So that's this function, and it puts because you've chosen an initial condition to get that function, that's fixed. All right. Okay, so let's try to understand this. This is a subtle problem. We're not going to worry about these are analytic curves. We're not going to worry about them just yet. So that same color scheme, and so thresholds are different. Now they're distributed according to a mean, a normal distribution, which is a bit funny because it's going to be 1 and 0. But the idea is that all of this stuff out here, if you have a negative threshold, then you just turn on for free. So that's a way of allowing that. And if you have a threshold greater than 1, then you never turn on. So that's the idea. It's a Gaussian distribution of thresholds. Right? Again, R is the term they used here. These three curves here, so again, this is the average degree of the random network, pure random networks again, a very different threshold, right? And this is for, so there's a typical spread of 0.2, and these are slices, so this is if you go up through 0.2, this is what it looks like, right, the final size. This is what it looks like if you go up around, so it's a bit funny, it's 0.362, which is so just through here. You see a what looks like a phase transition, right? Discontinuous phase transition. So this is pretty bad. So for whatever reason, your average degree of your network is moving, you're looking across networks in some way, then this is not so bad, but then it explodes. Nasty, right? But then you go a little bit further. If you increase the thresholds a little bit, so everyone has a slightly higher threshold, they become more resilient, then you get a benign looking thing like this. So you have to figure out where that comes from. So it's some kind of bifurcation thing has happened, right? Somehow, as you go across these slices, it's very subtle. It's in this little border here. There's a lot of this it looks like this a lot. Then it gets this very steep kind of feature to it here, and then eventually it sort of flattens out again. Right, so let's see if we can understand that. Okay, so this is actually a case where, so the initial, so no one's seeded, right? Because they have a general equation, right? They don't have to have anything seeded. So phi 0 is 0, but because of this, you have self-starters. So it just ignites, it spontaneously turns on. So effectively you have a phi 0 of some value. And we have this nasty phase transition. Let's see if we can understand that. Okay, so these are what the G functions look like now. This is not right. This is what the, okay. Yeah, you'll figure this out. This is what the stable points look like, stable and unstable points look like for the G function. Right, so sometimes G of 0 is a stable point. Let me go back to these pictures. Okay, so G of 0 is a stable point here. I mean, it's a fixed point. It's an unstable fixed point here. It's a fixed point here. It's not a fixed point here. So if this is a case where G isn't where 0 isn't a fixed point for all of these, it always takes off because of this. Right, it's always got some ability to spread. Well, what we're going to see is essentially, you imagine if this thing dropped down, right? Or, this is taking off like this, it's spreading a lot. You can imagine that this kind of waves and starts to drop down like this as well. You suddenly get big transitions in what can happen. And of course, if this thing goes below 1, another big possibility. So you'll have an assignment where you can you'll look across the G functions, you'll see them move such that they produce these fixed points, right? So this is a plot of the fixed points as we go across different networks. Okay, so for this guy, there's a fixed point, it's a stable fixed point that increases, right? It gets further and further, it's a larger proportion of the whole network. But 0 is never in there. So what happens for a small seed? You don't need a small seed. For seed 0, it always goes to here. Right? These plots are plots of this point as we change z. Or this point, and this point. Imagine plotting them as we change the networks. It's affecting, right? The network affects this structure because G has the network built into it.
We're plotting these.
The positions of these guys, if they exist, right? So the fixed points, the positions of these guys.
Oh, the positions, okay.
Yeah. So G has come before this. There's a G for each slice, right? For each Z, there's a G, and we plot its fixed points. Okay, so what happens is, as we change the threshold, this guy starts to push into here, right? This thing deforms, so it gets this shape, and it snaps, right? So eventually you get, instead of this being nice stable points connected to each other, it goes stable, unstable, and then back to stable. So what that means is, as you dial up through networks, this is the first guy you get to, because you're always starting at 0. So it goes to these points. Need some more. So you go to these fluids to it. So right, always you're starting at 0. So it's going to iterate up to the first stable point. Iterate up to the first stable point, first stable point, first stable point. When you get to here, because of this bifurcation, it goes, so suddenly the first stable point is up there. This is a nice, nice curve.
With the dotted line is unstable.
That's unstable, right? If for some reason you could start here, it would go down. Right? If you started anywhere in here, it would go down to here. Right? It would iterate down. If it started in here, it would iterate up. Yeah, but you can't start there because the initial condition is inherently connected to the function, right? So the initial condition for all of these G's is 0, just by construction. So it's 0 in all of them, and so 0 is always unstable. It always goes to the first stable fixed point. And because of this bifurcation, you can see it actually comes back here, which is kind of nice. So it actually becomes small again. So in fact, it's not shown on this picture, but there's another transition back this way, which is insane. Okay, so this one is benign because now this guy has gone here and connected to this. These guys have connected. So it's another kind of transition. These two have merged with each other. And so now you have a nice looking thing. So there's this stable point here and unstable point here. So let's see, that looks like, we get it wrong. So this is going to look like something like that kind of thing. So iterates would go up to here. So this is stable, and this is stable. Yep, I mean the positions are very different, but and this is unstable, right? Let's see if we can draw this one in the middle. So this one is just a nice stable point. That's fine. It's moving, but you can just imagine it looks like something like this. It's fine, and it just moves its location. However it does that, that's fine. It always finds this stable point. The one in the middle, let me see if I can figure what that is. So 0 is not a stable point. Okay. So what's happening is, so imagine you've got this picture, and then it goes like this. Right, so for some iterative before, it's like, for some, you're tuning the network, you're tuning the kinds of networks we're going on. So if this moves across here, the G function moves across here, suddenly there's no fixed point in the middle, and it goes to here, or to some value up here. So it's that little transition. Right, so this is a smooth transition in terms of this function. It's just smooth. But because as soon as that little, these two fixed points come together, they hit each other, and it moves off the y equals x line, then this opens up. And what's happening is we go through higher and higher degree networks, that in fact that, weirdly enough, this thing wiggles back down. It actually wiggles back down and makes this shape again. So it goes from, okay, so it goes from, say this to this, right, which means that it iterates all the way up. This one just stops, and then back, so it goes to this, and then back to something like this. So this guy moves back down and clips and creates two fixed points, right? So that's there's it's quite beautiful to be honest. But I mean, mathematically, what's happening is whether you're solving g of x equals x, right? Trying to find the fixed points of that equation. There's one solution. Now there are three solutions. And then now there's one solution. Right? That's three solutions. So, sneaky, nasty thing. But it's really about this thing wiggling around and whether it can release trajectories. Which, and so as soon as it just goes past it, it's very slow too. This is sort of a relic of intermittency, but very slow. It takes a long, if it's just off the y equals x line, that takes a long time to iterate through there, wriggling through it, which you can just see kind of graphically. No, it's total madness.
I think the first one made more sense for me than the third one.
This one.
Yeah, that one's kind of, I don't know why it's not sitting on.
As you're moving from here to here, this thing is merging. Makes that noise. Sono mathematics, I guess you can say. This one is, okay, so this one this one looks like, let me just make one. Well, it's not far off this, right? So it's something that looks like, okay, it's this, it has one fixed point. Let's say it has that. Yeah. Right, I mean, maybe one is one, it's fine. But it's got one interior fixed point. So it iterates to here, or to here. Then slowly that's always stays. As you move across all these networks, that's always there. But this does something like this. So now you get an unstable fixed point and a fixed point. And that's the emergence of these two here. Right? So this thing is moving around different ways, but the really key thing is this transition across here.
Oh, but that one always stays, so that's the right one, the one that always stays.
Yeah.
Oh,
It's always accessible. It didn't disappear.
okay.
So whenever you see these guys, right? Saddle node bifurcations?
Yeah.
Okay. Oh, look at that. Transcritical make you feel good? Pitchfork is good. Okay. The curve has crossed a line like that. Yeah, and they merge right here. Those fixed points merge at that point, and then they go off. And you have fixed, unstable, fixed. You always have that pattern. We'll see this for generalized contagion too. It's quite beautiful. But you always have that thing. So as soon as we pop past here, stable, and that's it.
Yeah, okay.
The ordering is always preserved. It always oscillates between the two. They come together and annihilate each other. That's another way to, if you feel like you weren't picked at sports when you were a kid. You like math and you want to use tough words. Okay. Very good. So we've talked about the single seed, but let's see if we can get it to work properly. Yeah. So you can think of the vulnerables as your initial set. It's a funny thing to do, I guess, but it's not quite right. I mean, obviously the spreading has to go through there. Order doesn't really matter. We can think of it happening at time t equals 0, and then we can rebuild these things. This is a bit rough. I wouldn't worry about this thing. Everything else is incredibly important. So we can rebuild those expressions. So this is yeah. I think actually this is think this is fine. Okay, so I'm just not going to worry about it. So, yeah, synchronous update is completely done. In fact, we have the complete time evolution of this spreading, which is enough. Asynchronous updates, and one way to do it is introduce a probability of not doing it locally. We did this with a super fun model that Cameron Harris put in. The hipster model. And so as alpha becomes smaller, right, so you have a probability of activating, as it becomes smaller, then effectively your chance of activating at the same time as someone in your neighborhood is 0, so they start to become independent. And it looks like asynchronous update. When it's 1, then you have synchronous, right? And you can talk about these guys. So that's possible. So that's good. Okay, that's pretty cool. Let's see. So let's talk a little bit. Let me just talk about diffusion. All right. So this is there's nothing about. This is elemental kind of contagion, right? Diffusion, just stuff spreading. So this is, again, it's going to be about edges and just a nice realization about those guys. There was about 8 months where Celia was lost. Turned out to be in a box of clothes somewhere. It was terrible. Everyone was sad. It was a disaster. It needs a wash, and that's a really big problem. Okay, so we're going to have just a plain network, and we're going to have a little random walker running around on this. Connects to the whole electricity business, actually, which is kind of fun. So we'll come back to that later on. Okay, so we're going to start some node J. Time's going to be discrete, and our poor little person who has no idea what they're doing is just going to wander around. So here's a question: where will they be in a long time, right? In a long time limit. And so in statistical mechanics, you call this what's the invariant density? So you take a dynamic problem and turn it into a geometric one, because eventually you get a probability distribution, right? So you get this flat picture of what it will be like in the long term. Yep. Okay. So. All right, so right, so we will want the cumulative thing. So eventually there'll be a transient. We want to kind of throw that away. Hopefully it sort of behaves what we call ergodically later on, right? So what's probably it's at node I? Okay. And we want to characterize how this is going to go. So we talked, of course, in POCs about standard random walks in 1 dimension, 2 dimensions, 3 dimensions, and how that's quite marvelous and good. Randomness is a spectacular thing. So we want to connect what's probably, so after some time t, there's a probability it's going to be at node 3, and probably it's node 12, and 30, right? And we can run all these things, and we'll have an ensemble of these walkers. Yeah? And we could actually set off a bazillion walkers at the same time, and they don't touch each other. We could think of it like that, right? Just let them run around and see where they all accumulate. That's another way to think about it. You could run parallel experiments or just have them sort of milling about. And that sort of milling about that's kind of classic diffusion, right? So you set up a big pile of stuff somewhere and see how it diffuses in space, right? So the classic diffusion thing is it flattens out like a nice Gaussian to start with. But it smooths it out, and eventually you get everything flat. Okay, we have Barrett. Baza. It's a good Australian one, actually. Baza. Okay. So he's far from home. He's on a high-dimensional graph. And he is completely drunk. Okay. So this is a bad situation for Baz. He is, okay, we're just going to think about simple networks. Right? They're not very random networks, they're just networks in general, right? They could have clustering, all sorts of stuff. But whenever Barry is at a node, we'll just choose randomly from the possible directions and then. All right.
So random walk is jumping from node to node?
Yeah, random walk on a graph. Yeah. Linear algebra time. Right? So we're going to have, right, this is our adjacency matrix. So there's a 1 if I has a, and we can make this directed, but let's think of it as being symmetric. So, as I said, right, this is just the definition of the thing. So in the next time step, right, it's going to randomly lurch from node J to one of J's neighbors. And so we'll turn this around. It'll be AJI, right? There'll be a 1 if J connects to I. Right? And the probability of getting to node I will be just simply 1 over Kj. Right? So it's uniformly distributed. Okay, so equation-wise is what it looks like. Let's make sure this is okay. So P of I, the probability that Barry is struggling around at node I at time t plus 1. So, well, had to be at a node from which there's a path from J to I in the previous time step. So you find all the nodes J, for which AJI essentially is 1, right? So it's going to be 0. It's just going to disappear if it's not connected. It's a 1 otherwise, and you get a 1 over Kj for each node J. Right, so if this node has only one friend and it's you, or it's this node, then Barry has to come back. Right, went out to that one node, has one connection, has to come straight back. If it's here and there are 1,000 friends, there's a 1 in 1,000 chance that it gets. Okay. All right, good, good, good. So we're going to have a vector, right? This is the finite network. Going to be n. Well, we could think about it a different way. N nodes. But there's a vector here, there's a vector here. This looks like a, what does this start to look like? This is a little stuff. But something like that. Sum over from J equals 1. What kind of thing is that? So sum, blob I equals a sum from J equals 1. A blob that has two things, J and I. And then a blob that has J. Yeah, it's a matrix equation type thing, right? And then we have to accommodate this guy, which is hanging around at the front. Okay. So let's try to make that a better thing. Okay, so this is also another thing we can say this to. So the degree of node K, node I, Ki, is the sum of it's the sum of the entries in the adjacency matrix in the ith row. Okay. Yeah. IJ. Ith row. Yep. So if stuff is being moved around a network, right? So yeah. So imagine. So this is the like many barriers, right? Lots of barriers. They're all in trouble. An infinite supply of barriers. But if we had stuff, if we thought it was just stuff, now it's a continuous amount of stuff. Right, so you have, I don't know. Okay, so you've got, water, right? So you've got so much water here in a bucket, and then you simply divide it by K, your number of friends, and give all of your friends that much water. And they all do the same at every time step as well. So there's sloshing all over the place. You've got pipes, like the internet, connected by pipes. And then things are sloshing around. Interesting question. So if it was normal diffusion, like you have water and it's all sloshing around, right? And it was just in a bath or right? Then it ends up being flat. Right? It's not driven anymore. Like imagine you started off with water like this and this and this. It goes swoop, 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 right? And it will flatten out eventually. It's diffusion. Yeah? So you might just expect that to be true on a network, right? So that every node ends up with the same amount of stuff. That would be the equilibrium state. Do you think so?
Everybody has the same amount of stuff.
Yeah. That's I'm luring. That's callous luring.
Is the equilibrium for the amount of stuff?
So given you have a quantity, whatever it is, doesn't matter, water, Q sub I at each guy. What's the equilibrium? What's the thing where it's all balanced? Such that from time step to time step, you pass off you divide your water up by your number of friends. You give them all a bucket, and they all give buckets of water. And every time step, everyone has the same amount in the next time step. It's balanced, right? It's reached equilibrium. How much would you have at each thing? It's going to be proportional to whatever, the total. So it's proportional to something. Think about that. Okay? Okay, so it's a stuff thing. So we have the same equation for stuff, right? Right? So random walking is, you know, somebody knows. So it's the same, you know, with random walking, one little random walker, many random walkers is different. And of course, random walkers can be classes. The normals, not normals. Okay. Linear algebra, yes. Okay. So we have this equation for our probabilities. So we can write it like this, actually. So we'll end up, so it's Ji instead of Aij. So that's J transpose. And this little sneaky guy, because it's 1 over Kj Pj, we can make that out of a particular matrix here, K, which we'll call Kij will be, in fact, just the degrees on the diagonal. Right. So the inverse of that is simple. It's the 1 over the degrees on the diagonal. So that's going to do the right thing, right? So if you have a diagonal matrix, it multiplies the p's. It's got 1 over the degree. It's got to give you this guy. Okay? So that's a sneaky way of doing it. Or the right way to do it. All right. So that's sitting in there. This is a diagonal matrix. This is our adjacency matrix. And so that's our update. Right? And this is good. This is pt plus 1. So we're going to be applying this blob over and over again. Right? This is our matrix. So over time, right, we apply this thing n times. Well, here it is. We want this guy, right? What's the dominant eigenvalue? That's the thing that's going to be picked out. And the eigenvector associated with that is the one that's going to end up being our distribution of water. Right, the other stuff is transient, and it will decay away. We'll end up with something like that. Cool. We want the eigenvalue's got to be 1, right? Things aren't going to go away from this, right? It's closed. Things are sloshing around. We're not going to grow water. We're not going to lose it. We're not going to grow probability of losing. We're not injecting things. We're starting off with some amount, right? Yeah. Okay. Okay, so that should be 1. This is just some intuition, and whatever the corresponding eigenvector is. And we can, we are very worried about is there more than one eigenvector associated with the number 1. It's terrifying. We want to see a gap in the eigenvalue spectrum. Okay. Well, that's so. There you go. We're worried about that. That can come from networks being if you have a disconnected network. That's not big enough. We want a connected one. We want Barry to visit everyone. All right. Okay. This is sneaky, but I'm going to tell you. So if you play around, we could try to solve this in all sorts of ways. But sit down and look at how this thing functions. It's going to look like this. So the infinite one, it's normalized here properly. It's the degree vector. Okay. So let's see how it works. So. Right, this is the diagonal matrix. So it's 1 over the degree everywhere. So if you multiply, what happens? 1 over K1, 1 over K2, 1 over K3, 1 over K4. You've got a vector, K1, K2, K3, K4. So what's that product?
1.
Ones. It's a vector of ones, right? Yeah. That's what you're going to say. Vector of ones, right? Good. So this is a vector of ones. A transpose times a vector of ones means sum up each row, right? Because a vector of ones means basically that says sum the rows of these things, and that gives you a new vector. And the sum of each row is
Sum of the columns.
it's the degree. It's a sum, and it's the sum across and it's the degree. It's the degree. So you get the degree back, which is what we said we were doing. K1, K2, K3, K4. So, this is not, because, this isn't some horrible thing that we can see what it is. We can somewhat naughtily figure out what it is. So this is a really cool result, right? So probably the barriers, so, the hubs is where Barry will be, proportional to their degree. It's a very nice result. So that's just a really important thing to know about, right? Okay. And then there's a very beautiful thing, which is probably that barriers actually on any particular link, though, is uniform. So there's no favoritism for the links. So when you move away from, okay, so we have this idea of water in a thing being shaken or starting like unevenly, and then you let it go. It smooths out. So if you kind of start to think of that as a network, right, of space, just a grid, then the water ends up being equally in all the nodes. And then, if there's sort of stuff moving around still, maybe it's air, then, you can imagine air in a box, then it's still, it's on all the edges as well in a uniform way. It's really edge space where diffusion becomes uniform. And you have to go to networks to see that, because in normal space, right, the dual thing, like the edge and the nodes are sort of the same structure. There's nothing interesting about that, right? So it ends up, the water ends up being uniformly distributed in space and kind of on the edges between the space, if you think of gridding it. But it's really, if you have a network, it's really that it's being uniformly distributed on the edges. So it's flowing around back and forth, the sloshing. So all the edges look the same, but that means you get accumulations proportional to degrees. Okay, so, diffusion smooths things out. The smoothing out on networks is in edges. So it's really about the edges. You just don't see that. Right? So again, it's about edges. Always about edges. Intent. Both analytically better to think about edges, and and the reality is that that's where things matter. All right. There's one little bit to add, and then we can go. But this random walk stuff, we'll use this again when we think about measuring things like betweenness and so on. Right? So it's an important measure. It actually then connects into thinking about, well, how do we, we've got some monstrous network. How do you figure out what the macro structure is? You can, this is a little extra. That's okay. Similar matrices are similar. It's not a bad thing. It's a beautiful little piece. So if it's a symmetric matrix, AA transpose, which is fine for these undirected networks. So if we take this guy, mk minus a half, then we can put m minus 1, like this. That gets this guy here. And since we have this, we have A transpose equals A, right? So we can just replace that guy there. And the last thing is, did I do the wrong thing? Right, okay. So the point is, we're connecting it to a it's harder to see it here, A transpose K minus 1. We're going to connect it to, we're going to say, make a similarity transformation to another matrix, this guy. And then if you take the transpose of this blob, you get the same thing, right? So transposes, right? So if you have ABC, it's CBA, C transpose B transpose A transpose. These are diagonals, so they're the same. A is A transpose. So this whole thing that we've moved to, just, it's a bit of a funny thing, but we've moved to something where we can see that it's symmetric. So then we know, we have real eigenvectors and all those things. So orthogonal symmetric matrices are beautiful things. They're the best. And you can show the maximum eigenvalue is 1. So that's really all there is to that. Anyway, just this is a really nice little piece, just basically about networks. We're going to move on to we have to think about assortativity, right? So now we want to tweak our networks and say, there's a proclivity for degrees, nodes of different degrees. We've talked about this homophily and so on. We want to build that in, bake that in, and then think about spreading on those things as well, and think about more general kinds of networks as well. And then we'll get into some of these. Well, there's a few of them. No, there's a lot of contagion. Yeah. Keep going. All right, well done. Excellent people. Thank you for overcoming. Surviving. All right. Good. We should go and build that. Oh, there's a quality.